In this third lesson on radians, we're going to have a look at something called small angle approximations. And just to get started, I want to have a look at the graphs of sine, cos and tan, but just at very small angles and see what's going on. So here is the graph of sine x. Notice that I've plotted it in radians here. Perhaps if I change my axes, there we go, that shows a bit more clearly that I'm working radians. Now, if I look at really small angles, so maybe down here, they follow almost a straight line, which is interesting. So let's see if they are actually a straight line. If we plot y equals x, then I can see that actually this is very, very close to being a straight line. In fact, I'd say, I suppose it depends how much you zoom in, but maybe between 0 and, I don't know, pi over 3 or so, sorry, pi over 12, so about halfway through this box, it basically does follow y equals x. So it's reasonable to say that when x is a really small angle, we can actually just estimate sine x as just x. So for example, if I put in this value here, 0.0654, I could estimate the y value as 0.0654. I wouldn't actually have to work out sine of that value because it's pretty much on the line. So this is quite a useful approximation because if you know that you're only dealing with really, really small angles, then rather than calculating sine x, you can just calculate x, which is obviously saves you some work. If you're writing a program or something like that, it saves you a bit of computing power. Let's have a look at, we're going to look at tan x first, I think, actually, because tan x is actually more similar. Tan x, again, we've got a section of this graph which looks a bit like a straight line. Let's have a look. Well, again, y equals x, that pretty much follows it. It's only about here where it starts to diverge. So again, for really small angles, I could say that tan x is approximately just x, so maybe between here and here. We normally tend to say it's about 0.1 radians. Okay, that tends to be where these are valid. If I tell you that pi over 3 radians, that's roughly 1 and a bit radians. But if we go for 0.1 radians, if I draw the line x equals 0.1, certainly in this section we can regard this as a pretty good estimate up to here. Okay. Now if we look at cosine x, like this, well, it's clearly not going to be y equals x. It definitely doesn't follow that line. Y equals minus x maybe. I suppose it goes downwards, so that kind of helps. I think this looks more like a negative quadratic, so maybe something like minus x squared. It's obviously in the wrong sort of place. It's the right sort of shape, but it's in the wrong place. Let's just change the color of this as well. Okay. So maybe if we move it up by 1, so it starts there, that's not too bad, is it? But I think we need to stretch it outwards as well to make it fit better. So I'm going to stretch it outwards. If I stretch it outwards by 2, I could replace my x with an x over 2. Like that. In fact, I don't want the over 2 in there. I just want it to be x squared over 2. X squared over 2. There we go. That's a much better fit. So if we look at this one from about 0.1 or less, in this region here, you can see the blue line and the red line, they're basically on top of each other. You could probably make it a bit more to the right if you wanted to, but not too far because then they do start to diverge. But anything less than about 0.1, it's quite reasonable to assume that instead of cos x, I could use this function here as an estimate instead. 1 minus x squared over 2. And these are what we call our small angle approximations. Okay. So these are the graphs that we looked at. It's also important that this only works when we're working in radians. If I plotted the graphs in degrees instead, so on Desmos I can just change the settings and just plot it in degrees instead, you can see that this doesn't really work. Okay, just because the scale is so different between degrees and radians. Okay, if we're dealing with pi radians, that's 3.14 degrees. That's not going to quite work in the same way. So these only apply when we're working in radians. So on the left here, I've got the sine graph in radians. On the right here, I've got it in degrees, and you can see that it doesn't really work as an estimate here. But we showed that when theta was really small, so sort of smaller than 0.1, 0.2, sine theta, you can approximate it as just theta. And the same with tan theta, that approximates to just theta as well. And then cos theta becomes 1 minus theta squared over 2. And you are given these in the formula booklet, which is quite handy. Okay, so it's helpful to remember them, but they are in the formula booklet. We're also going to have a quick look at how we can derive these. Rather than just looking at the graphs and sort of estimating it, how can we actually derive these a bit more mathematically using some geometry? So here I've got a diagram. I've got a triangle. This is quite similar to what we looked at when we were doing sectors and arcs as well, this kind of diagram. So I've got a triangle, but I've also got a sector in here, and I've also got a tangent. And I'm just going to label a few points. We're going to set up a bit of a geometric problem to show another way in which we can arrive at these small angle approximations. Okay, so I've just labelled my points O, P, and Q. And then this is also T, where it meets the tangent. And then this is obviously the radius, and this is also the radius. You can also see that OTP is a right angled triangle. So this is a right angle down here, because it's where the circle or where the radius meets the tangent. So that means that this length here, TP, I could actually calculate that as being r tan theta. Okay, the reason for that, if you think about tan theta is opposite over adjacent. This is my opposite here, t to p, and my adjacent is r. So I can say that tan theta is t to p over r, or if I rearrange that, this is r tan theta. Now what we're going to do here is we're going to look at 3 different areas that are on here. And again, this is a bit like when we did sectors and arcs before. So if we look at the area OPQ, okay, now the area OPQ, that is a triangle. Okay, or sorry, we're going to look at the sector first actually. Let's write this as sector. Then we'll look at the triangle OPQ in a minute. So the sector OPQ is half r squared theta. The area OPQ, but as a triangle, so obviously with the straight edge instead, that would also be half r squared, because half AB sine theta is what I'm doing for the area of a triangle. So AB, they're both r, so it's half r squared sine theta. And we're also going to look at the area of OPT, which is a big triangle. Okay, so that's O to P to T, so that's the right angle triangle. Now that one, because it's a right angle triangle, we can just use half base times height. So that'd be half times the base, which is r, times the height, which is r tan theta. So that would then give me r squared tan theta. Okay. Now what we're going to do is we're going to consider what happens to these 3 areas. So that's the area of the triangle, the area of the sector, and the area of the right angle triangle, as I make theta really, really small. And I've got a little animation to show you this. I know this red tangent line is slightly different to the one that we've got, but it's the same idea. But look at what happens as I make the angle smaller. So here they're quite different, these 3 areas. But the smaller that I make the angle, the more similar these 3 areas are going to become, until you almost can't tell the difference. If I put it there, they're very similar areas. If I put it here, well, I can't even spot the difference really. They're very similar. Until you get so small that these 3 areas become similar. So we can say that as theta tends to 0, the areas tend to be the same. Okay, so as theta tends to 0, the areas of these 3 shapes tend towards the same value. So we can then say that half r squared theta, actually I won't write equals, I'll use a little wiggly equals sign for approximately equal to half r squared sine theta which is approximately equal to half r squared tan theta. And you can see I've got a half r squared in each of these terms, which I can then divide through by. So theta is approximately sine theta, which is approximately tan theta. And that gives us our first small angle approximation, but through a geometric means rather than a graph. We're going to do the same sort of thing for the cosine one now. So on this one, rather than looking at areas, we're actually going to look at the arc lengths involved. Now again, I'm just going to label this triangle in a specific way. Okay, so those are the points O, R, and P, and then Q. I'm going to label this angle as theta, and this time we're just going to consider it as a unit circle. You can do it with a radius r, but it makes the algebra a bit easier if we consider it as a unit circle. Okay. Now, another line that I want to look at in here is the line Q to P, like that. Okay. Now, what I want to think about here is as theta becomes smaller and smaller again, this straight line here, the dashed line Q to P, is going to become very similar in length to this curved line here, Q to P. Again, I'll show you what that looks like. So here's this shape. As the angle becomes smaller and smaller, this blue line and the green curved line are going to become more and more similar. And you can see their lengths, I've written them on there. Okay, here they're very similar in length. Here they're both 0.22. Once we get to about 0.1 radians, they are very similar indeed, 0.097. Okay, until actually you can't visually see the difference anymore. So what we can say here is as theta tends to 0, so it gets very, very small, we can say that the arc Q to P becomes very similar in size to the line QP. Okay. Now we just need to come up with some expressions to describe the length of this arc and the line QP. Well, the length of this arc, we know that arc length is r theta. So in this case, it's going to be 1 times theta, so that's just theta. Now the straight line Q to P, we need a bit more information for that. Let's see what other lengths we can label. Well, O to R, that bit there, that would be at cos theta. Okay, if I have this as a right angle triangle here, I've got the hypotenuse and I want to find the adjacent. So that's going to be 1 cos theta, which is obviously just cos theta. This length here, this vertical one here, Q to R, that's going to be sine theta. Okay. Because again, this is the opposite and I've got the hypotenuse, so it's 1 sine theta for this length here. That means that this length in here, R to P, well, the whole radius is 1, and this bit's cos theta, so this is just going to be 1 minus cos theta. That bit in there. Well, now I can find length Q to P if I draw this right angled triangle out. Like that. So this is point R, this is point P, and this is point Q. We said this length was sine theta, and this length was 1 minus cos theta. So line Q to P, we can use Pythagoras, because right angled triangle. It's going to be sine theta squared plus 1 minus cos theta squared, and then square rooted. Okay. Now let's see if we can use this statement here to come up with our small angle approximation. So we're saying that as theta becomes really small, the arc Q to P, which is theta, becomes the same as the line Q to P, which we've described as this. Okay. So maybe I'll start by squaring both sides, just to get rid of that square root. So I've got theta squared equals sine squared theta plus, and maybe I'll expand this bracket whilst I'm here, so that'll be 1 minus 2 cos theta plus cos squared theta. And then I can do some rearranging here. I've got a sine squared plus a cos squared. So sine squared plus cos squared, that makes 1. So I've got 1 plus this thing here still. So theta squared is 2 minus 2 cos theta. And bear in mind, I'm trying to get to cos theta equals something. So theta squared over 2 is 1 minus cos theta, which means that cos theta is 1 minus theta squared over 2, which is what our small angle approximation was from earlier on. So again, we've got a nice geometric proof of this small angle approximation here. So just to remind ourselves what the approximations are, we've got sine theta approximates to theta. Tan theta approximates to theta as well. This is when theta is small. Okay, I would generally say that theta should be less than 0.1 radians. And cos theta approximates to 1 minus theta squared over 2. Okay. And we do get given those in the formula booklet. Okay. So I mentioned earlier on that this has to work in radians. Okay. And if we change the scale, then it just doesn't work at all. Another reason why it doesn't work if you do it in degrees is because think about the geometric proofs that we just did. They relied on the formulae that worked in radians. So like the sector area formula and the arc length formula. That wouldn't have worked if I did it in degrees. And when we come on to look at differentiating and integrating trig later on in year 2, these small angle approximations are really useful as well. Right, let's look at a couple of examples of how we can use these to simplify some expressions. So if we look at A, we've got sine 2 theta plus tan theta over 2 theta. So that's going to become, when theta is small, instead of sine 2 theta, that's just going to become 2 theta. Okay, because remember, sine theta just becomes theta. So when it's 2 theta, it's just going to become 2 theta. Tan theta, that will approximate to just theta. This thing on the bottom, well, that will stay like that. So this is going to approximate to 3 over 2. Okay, and that's obviously much simpler than this expression here. B, cos 4 theta minus 1 over theta times sine 2 theta. Now again, the approximation for cos was cos theta approximates to 1 minus theta squared over 2. Let's look at how that applies here. Instead of theta, we've got cos 4 theta. So this is going to simplify to 1 minus, instead of theta, it's going to be 4 theta squared, and it's the whole thing squared, divided by 2. And then I've still got that minus 1 as well. Divided by theta times sine 2 theta. Well, that will approximate to just 2 theta. And now we can try and simplify this. So I've got 1 minus that and minus 1. So that's just going to give me minus this thing here. So that'd be minus 16 theta squared over 2. On the bottom, I'm going to have 2 theta squared. On the top, if I simplify that some more, I'm going to get minus 8 theta squared divided by 2 theta squared. And you can see these theta squareds are going to cancel out. So let's get minus 8 over 2. So that's then minus 4. Okay, so the thing to go careful of here is that instead of theta, I've got 4 theta. So it needs to be 4 theta, and then that's that whole term there being squared. So you get 16 theta squared. Okay, that's normally the place where people go wrong in these questions. Right, here's another example. So show that sine 5 theta plus tan 2 theta minus cos 2 theta equals this. Let's just write down our approximations. So sine theta and tan theta, they both approximate to the same thing. They both become theta. cos theta will approximate to 1 minus theta squared over 2. So sine 5 theta, that's just going to become 5 theta, plus tan 2 theta, well, that's going to become 2 theta, minus cos 2 theta, that's going to be minus, let's put this in a bracket, 1 minus 2 theta all squared over 2. So I've then got 7 theta for the first two terms, and I've got minus, this bracket is going to be 1 minus 4 theta squared over 2. Okay, because I've got 2 theta all squared. So this is then 7 theta minus 1, and then plus, well, this would just be 2 theta squared, because 4 theta squared over 2 is 2 theta squared. So I'm then left with 2 theta squared plus 7 theta minus 1, which is the expression they were after. In part B, hence state approximate value of this for small values of theta. Well, this is the same expression as we had before. So we want to think about what happens to this expression when theta is really small. So basically what we want to find is the limit as theta tends to 0 of 2 theta squared plus 7 theta minus 1. Well, as theta becomes really, really small, this is basically going to just become minus 1. Okay? Simple as that. Right, here's an exam question. So here we've got to show that when theta is small, we can rewrite this expression as this one here. Let's just do this underneath so I've got a bit more room. So the first thing to do is replace cos theta with its approximations. That's 1 minus theta squared over 2 minus sine of a half theta. Remember that it just approximates to whatever the angle is. So that's going to be minus half theta. And then plus 2 tan theta, so that's going to be plus 2 times tan theta approximates to just theta. And now it's just about simplifying this. So I've got minus a half theta squared. Then I've got 2 theta minus a half theta. So that's going to be plus 3 over 2 theta. Then plus 1 equals 11 over 10. Then I'm just going to subtract 11 over 10 from both sides. So it's like 1 minus 11 over 10, which is minus 0.1. So we've got to there, we've got to get it to having a 5 theta squared at the front and a plus 1 at the end. So I think I'm just going to times it all by 10. So if I times this all by 10, then I'll get minus 5 theta squared plus 15 theta minus 1 equals 0, and then just times it by negative 1. Okay, so we've got to that as our final answer, which is what they're after. Now it says the solutions of the equation thing that we just found are 0.068 and 2.932, to correct to 3 decimal places. Comment on the validity of each of these values as approximate solutions to the first equation. Well, if we're trying to solve this equation here, and we're using this one, this only applies when theta is small. Okay. Now, if you remember from before, I said that theta should be about probably less than 0.1. Okay. So this solution is fine. This one is not going to be valid because it's much, much bigger. You definitely wouldn't consider almost 3 radians to be a small number of radians. That's on the graph. If you think back to the graph, that's going to be quite far to the right. It's not actually going to look like a straight line in that portion, for example. So in terms of the validity, 0.068 is valid because it's a small angle. 2.932 is not valid because it's definitely not a small angle. And our equation that we simplified it to, this only is true for small values of theta. Okay, let's have a go at a couple of questions about small angle approximations. Have a look at exercise 5F.